Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here. We're doing engineering calculus tutorials. Chapter 0 is things you should already know. Basically, this is all the appendices and those types of things where they're expecting coming in there. You've already seen this somewhere in K to 12 or K to 13 if you're from Ontario. But this lecture specifically, what we're going to do is we're going to discuss intervals, notation, and solving inequalities. Let's get to it. All right, this one's Jasper. All right, so what an interval is all real numbers x that are between two fixed numbers a less than b. We will use the following notation. So we're going to use interval notation, set builder notation, and the real number line notation. We can map the set of all real numbers onto the real number line, and then pictorially we have a representation of this also. So what's an open interval? An open interval is an interval, a finite open interval. There's a few other open intervals in here somewhere, but the finite open interval is AB, where we use round brackets, and what that means is real numbers that are strictly between A and B, but you can't equal A and you can't equal B. And on the real number line, what we do is we denote this as we mark A and B, and then we get the interval between A and B, all these real numbers, but you're not allowed to equal A, you're not allowed to equal B, so this is an open circle. A closed interval, a finite closed interval, is going to be AB, where we use square brackets now. And what that means is all real numbers that are less than or equal to A and B. So now you're allowed to equal A and you're allowed to equal B. And so pictorially, we have the interval between A and B, and then you're allowed to, we fill the bullet in each case because you're allowed to equal A and B. So essentially what that means is in our notation, these three things are the same thing. Square bracket means less than or equals, which means you're allowed to equal the value A or B, whichever one you're dealing with. And round bracket means strict inequality, and that means you're not allowed to equal that value, so we use an open circle on the real number line. The other intervals that we have are these variants of intervals where we have a closed interval, half open, half closed, or we have where B is in positive infinity or where A is possibly negative infinity. Pause here if you want, but this is all the possible combinations of intervals which are subsets of the real numbers. Let's do a couple examples. All right, example 1, find the union and intersection of these two intervals I1 and I2 in each case. The first ones we've got are I1 is -1, 2, and I2 is 0, 5. So we have some closed parts, some open parts. So let's see how to do this. The best way to do this is what we're going to do is draw the real number line twice. What we can do on the first one is we're going to, on both of them, we're going to mark 0 in the same spot, the origin. Then we can mark off these two guys. So what we have is -1, and then we have 1, 2, 3, 4, 5. This is negative infinity. This is positive infinity. And so same thing down here, 1, 2, 3, 4, 5, -1. Once I have that, I can now pictorially represent both of these intervals individually, and then I can nicely visually find their intersection or their overlaps and then their unions. So what that's going to give me is, for the first set, I have -1 open and then 2 closed and all the points in between. This is I1, and I2 is now 0, which I'm allowed to equal, and then up to 5, which I'm not allowed to equal, so it's open, that end point. And so this is I2, and then what I can do with that is for the union and the intersection, what we can do is look at, for the union, first of all, it's in OR. So what we do is we take the lower points, endpoints, and we pick the lowest one and the associated bracket with that. So at -1 we have open, and then for the top points, what we're going to have is it's allowed to be in either of them, and since they overlap, you're going to pick the largest value. So we're going to pick 5 and the open value, and then we see that the union of two intervals that overlap is the larger interval with the endpoints and their associated values. So this is an open interval. This is the interval -1, 5, which is I1 union I2. And then for their intersection, it has to be in their overlap. So it has to be anything that's in both of them. And so the best way to do that is from there, I have 0, 1, 2. And so in this one, we have 0 is in both of them. And then in this one, 2 is in both of them. So this is I1 intersect I2, and it is the interval 0, 2. But let's erase and then we'll do the next one. All right, again, so you don't need to watch me do that. There we have the 4 intervals that we're going to do for the union and intersection, and then the original 2 intervals. First of all, who do I have? I1 is going to be, this is I1, so we're going to do it in blue, and that is -infinity to -1, not including -1. So that is everything in there, ... So this is I1. For I2, this is I2, -2, 4. Both of them are closed brackets, so we're allowed to equal both of those values. So we have -2 and we have 4, and that is everything in between -2 and 4, so a closed interval. This is I2. For their union, I1 union I2, what is that? It's anything in either of them, so it can be anything from -infinity to 4. All of these points, and so that is going to be -infinity 4 square bracket. For their intersection, it's where they overlap. So where they overlap, it's going to be -2, and then 1 is not in this one, so we have to use open circle. So this is their intersection, so I1 intersect I2 this time is -2, -1 round bracket. Let's do more. All right, let's move to inequalities. First we'll list the properties, then I'll do a couple examples, and then we'll start solving inequalities. Next video, what we're going to do is solve absolute value inequalities, but first let's deal with linear and nonlinear inequalities. The properties, basically what this is, A and B originally are real numbers, but then eventually we can replace these in fact with any functions of x or anything else, and we can change the expressions. These rules are essentially true as long as we're doing this in the real numbers. The expressions can get much more complicated than this. I'll do a couple examples. First of all, what are the inequality properties? The 2 most important ones I've highlighted, but for us, first of all, if you have A is less than B, then you can add or subtract C to both sides and it doesn't change the order of the inequality. This is good. If you have 2 inequalities, if A is less than B and C is less than D, when you add these, it will preserve the inequality, so A plus C will always be less than B plus D. And the nice one that you don't have to think about is if A is less than B and C is positive, when you multiply both sides, the order stays the same. Number 4 is the one that gets you every time. If A is less than B and C is negative, then the order of the inequality changes. And the best way to see that is if I have, here's 0, then I have 1 and 2, and -1 and -2. So if I pick 1 is less than 2 and pick C equals -1, which is less than 0, if I multiply both of the sides of this equation by -1, that should give me that -1 is larger than -2, which it is. So I always do these. If you don't like the mumbo jumbo, do an example with some numbers and see intuitively at least if it's matching what this is trying to say for us. For this one, what it also is going to say is if both of these numbers are positive and A is less than B, then we can reciprocate, and the reciprocal's 1 over B. The reciprocal of B is less than the reciprocal of A, so the order changes again. And then what I do with this to make it non-trivial is just look at 0, 1, 2, and 3. So look at 2 is less than 3. But if I now look at 1/2 and 1/3, 1/3 is less than 1/2. So when I reciprocate, the order changes. And this one I just can't help myself, but this is what we used in the last video to find the closer guesses to the approximation of the square root of 5 anytime you have an interval a and b. In fact, a plus b over 2 is the midpoint of that interval, so in particular it's strictly less than both of the values. All right, let's do a couple of examples. The first one, example 2, is find all x in R such that this inequality holds true. So what we can do with this is we can use the rules that we just listed, or the properties that we just listed. So what are they? We can add or subtract on both sides. If we multiply both sides by -1/2 at some point, we're going to have to flip the inequality, etc., etc. So starting with this, solution 1, say, what I'm going to do is work not so smart, or then I have to remember all the properties. What that's going to do for me is I have 4 minus 2x is greater than or equal to -6. I can subtract 4 from both sides, or add -4, and what that says is, therefore, if and only if these ones will cancel, that says -2x is greater than or equal to -6 plus -4 is -10. And now I want to multiply both sides by -1/2, and what that's going to do for me is give me x is less than or equal to now -10 over -2, which is 5. So that says that x is strictly less than or equal to 5. And on the real number line, that says that we are going to be, here's 0 and here's 5, less than or equal. We have, this is all the real numbers. As another solution, solution 2, what I can do is try to work smart and put the x by adding on the right side, and then I never have to multiply and by a negative number and remember to flip the inequality. So this time I have 4 minus 2x is greater than or equal to -6. This time I'm going to add 2x to both sides. So that's going to give me 4 is less than or equal to -6 plus 2x. I'm doing it one at a time. Then I'm going to add 6 to both sides. So what that tells me is 10 is greater than or equal to 2x. And then now I don't have to worry about flipping the inequality because 2 is positive. So I'm going to multiply by 1/2, and that says 10 over 2 is greater than or equal to x, or 5 is greater than or equal to x. And so again, that gives us 0 and 5. And on that interval, we see that it says less than or equal to 5. So this is our interval in either case. All right, for the next one, what we want to do is show that x to the 4 over x to the 6 plus 3x squared plus 1 is greater than or equal to, or less than or equal to 1 over x squared. These are extremely useful in engineering calculus 2 when we do power series, etc., and we have to use comparison tests and all those types of things, or in limits. And what we can see with this is, what I want to use is property 5, essentially of reciprocals. So first of all, what I'm going to do is show that x to the 6 plus 3x squared plus 1 is greater than or equal to x to the 6. If I add two positive terms to something that's already positive, then it's definitely going to be larger or equal. And then what that's going to tell me is, by property 5, by reciprocating, that tells me that 1 over x to the 6 plus 3x squared plus 1 is less than or equal to 1 over x to the 6. And since x to the 4 is greater than or equal to 0, we can multiply both sides by x to the 4, and it doesn't change the inequality. So that tells me that x to the 4 over x to the 6 plus 3x squared plus 1 is less than or equal to x to the 4 over x to the 6, which is 1 over x squared. Therefore, we've used the properties of inequalities to show that this horrible beast is less than this, and then when we do this in power series, we can say that both of these are convergent by the comparison test. These are the inequalities. Anytime you get something, it might look drastically different, but the rules are, the properties of inequalities are the only ones that you're allowed to use. All right, so now let's solve. This is actually solving, this is our segue sort of, this is solving a linear inequality for x. Now what we're going to do is solve linear and non-linear inequalities in general. Let's do that. All right, when we're solving linear inequalities, the most general form is going to be ax plus b is less than or equal to cx plus d. without lots of generality, you can flip that around, but we don't know whether A and B and C and D are positive or negative. But here's an example of one. These ones, the idea is going to be solving linear ones is fairly easy. Solving nonlinear ones can be hard, but the idea is going to be breaking it into linear components or irreducible quadratic components and then finding out the sign and then multiplying them back together to find out the overall sign of the nonlinear inequalities. So for linear ones, what do we have? Example 4 is solve 2 plus x is less than or equal to 4x plus 3. I want to work smart and not hard, so I'm going to bring the x to this side and the 3 to that side. So this is if and only if I'm going to do 2 minus 3 is less than or equal to 4x minus x. So I've added x to both, or I've subtracted x from both sides, and I've subtracted 3 from both sides, canceling the x on this side, canceling the 3 on this side. What that gives me is, if and only if I just clean this up, this is negative 1 is less than or equal to 3x. 3 is positive, so I can multiply both sides by 1/3. And that won't change the inequality. That gives me negative 1/3 is less than or equal to x. And that is the interval that we have. What is that? On the real number line now, we have 0 and negative 1/3. And we are greater than or equal to negative 1/3. So we're allowed to equal that. And we are this interval. This is all real numbers that satisfy this original inequality. All right, let's move on to nonlinear inequalities. Again, the strategy is going to be breaking it into linear parts or irreducible quadratic parts, and then looking at the sign of each of those, multiplying the signs back together, and then knowing whether something is greater than or equal to 0 or less than or equal to 0. Let's do that. All right, for solving nonlinear inequalities, what we're going to do is we're going to usually have some kind of rational function in x, say we're going to call it r of x. What that means is r of x is the ratio of two polynomials. What are polynomials? Powers of positive integer powers of x and then sums of them. So for example, another rational function is the polynomial 1 over the polynomial x squared plus 1, or this rational function is the polynomial degree 3x cubed minus 1 over the degree 2 polynomial x squared plus 5x plus 6. So we're going to have some expression, and then what we're going to do to solve nonlinear inequalities, we're going to move everything to one side, and then it'll be less than 0 or greater than 0. And then what we're going to do is we want to know whether this thing is positive or negative. So what we're going to do is we're going to split this rational function into all of its linear or irreducible quadratic terms. Irreducible quadratic means you can't factor it over the real numbers, x squared plus 1 or x squared plus x plus 2. And you look at the discriminant to see if this is negative, and if it is, you have no real root, so you can't factor it. This allows us to find the overall sign of r of x by looking at the overall sign of each of these individual simpler factors and then multiplying those together to get the overall sign of r of x in each case. So, for example, x cubed minus x, we can actually cleverly factor as x, x plus 1, x minus 1. Then we can look at, if we're on some interval, we can look at when this is positive or negative, this is positive or negative, this is positive or negative. Then we multiply them all together and find out whether this thing is positive or negative on that interval. Let's do a couple examples using that guy specifically. All right, solve the nonlinear inequality x cubed is greater than or equal to x. What we're going to do with this, first of all, pictorially, graphically, if we know what this means already, if I draw x cubed, we're going to do this in later videos what all these things look like, but this is x cubed. And then we have the straight line y equals x, and that's going to look like that. And so there's going to be these 3 intersection points. And then we're going to find out, what we're asking is when is x cubed larger than x? So it looks like this happens at negative 1 and this is at 1. This is our 0. So it looks like between negative 1 and 0, we're larger. This inequality is true. And it looks like after 1 to infinity, x cubed is again larger. What we're going to do with that is we're going to draw another picture and solve an inequality. But for now, that's graphically what we're actually asking in this inequality. When is the graph of the function x cubed larger than, greater than or equal to the graph of the function y equals x? What we're going to do with this inequality is bring everything to one side, factor it, split it into linear factors or irreducible quadratics, find out the sign of each one and on each interval of the real number line, and then find out which ones we keep and which ones we throw away, which intervals we keep and which intervals we throw away. So we have x cubed is greater than or equal to x if and only if x cubed minus x is greater than or equal to 0. first rule of factoring. If I have x in both terms, factor it out. So if and only if x squared minus 1 is greater than or equal to 0, I have a difference of squares. This is going to give me x plus 1, x minus 1 is greater than or equal to 0. Now this is equivalent to this statement. I want to know when this statement is true. When is that statement true? That statement is true if and only if. What I'm going to do is, when is this equal to 0? At 0, at -1, and at 1. So what I'm going to do is I'm going to split the real number line into those values. I like to draw a nice little chart for myself. And then what we're going to have is I have negative infinity to my first root, -1. This guy, negative infinity to -1. Then I have -1 to 0, my next root, this interval. Then I have 0 to 1, this interval. And then I have 1 to infinity. So I've split the real number line into those intervals where I have 0 exactly. And now I want to know when I'm greater than or equal to 0. What I do is I list all my linear factors. And then this is x cubed minus x, which is their product. And I want to know, and I want that to be greater than or equal to 0. So now with this chart, what I can systematically do is make it look pretty first. And then once I do that, I fill in systematically the signs of each one. So also to help myself, -1, 0, 1, not the scale, 0, 1. So I have these intervals also. And then what I want to know is the only place I can change signs is at -1 and at 0 and at 1. So in there, in these intervals, I just need to pick a representative in there. In here, I'm going to pick -2 in this interval, negative infinity to -1, this interval. In there, once I pick that representative, -2 plus 1 is negative. All I need is a sign. -2 is a negative number, and -2 minus 1 is negative. So I have 3 negatives when I'm in this interval. All 3 of these terms are negative, these factors. But when I multiply them together, I get this thing is going to be, these 2 negatives give me a positive, but the overall sign is going to stay negative, and that's not what we wanted. And again, that graphically says that it's not true here. Then what we're going to do next is in the next interval, in here, we're going to pick a number, say -1/2. There's a moth in here. It's a ladybug. Ladybug. Got you, ladybug. Got him. Oh, there he goes. Ladybug. Alright, so in this interval I'm going to pick -1/2. -1/2 plus 1 is positive this time. -1/2 is still negative. And -1/2 minus 1 is still negative. 3/2. So I get these 2 are positive and this is positive. So I do get positive this time. And that's what we wanted. And of course, graphically, it told us that originally. Then what I'm going to do is pick a number in here. Again, 1/2 is good. Nice, easy numbers. In here, 1/2 plus 1 is positive. 1/2 is now positive. What 1/2 minus 1 is -1/2, which is still negative. So when we multiply these together, I get overall sign is negative in here. And then this is not what we wanted. So we throw that interval away. Then what I do is in the last one, I pick some representative 2 in there, say. 2 plus 1 is positive, 2 is positive, and now 2 minus 1 is 1, which is positive, so everything is positive, and I want to keep that one. So the intervals that I'm going to have now, what that tells me is x cubed is greater than or equal to x if and only if x is in the intervals, which one? It's allowed to be in this one, and a greater than or equal tells me I'm allowed to equal the endpoint, so I'm going to use square brackets, -1 to 0, union, because I'm allowed to be in that one, or in this one, which will be -1, which I'm allowed to equal, and then infinity, so I'm going to get -1, infinity. This is how we solve nonlinear inequalities. We'll do a bunch more next time, and then what we're going to do is continue on with more nonlinear inequalities, and then we'll do absolute values, and then absolute value inequalities with nonlinear factors in there, and then we'll move on from there. Please subscribe right here, hit the notification bell. I'll see you next time.